Right, so I'm hoping exams will be graded by the end of the week. I know the drop deadline is Friday. Of course, the TAs have a lot going on, so ask them to do their best to at least get most of it graded. So if you do have concerns and you want to come talk to me about them, we can take a look at how your score was looking up to that point. Just going to have a little bit of discussion about maybe things that you're having a little bit of trouble with that was reflected in the exam. So I have looked at question 13 and question 5. So question 13 was that take-home one with the plotted points showing convolution. That looked pretty good for the most part. There's a couple that kind of, I think, got confused between frequency domain and time domain and thought it looked like a bandpass filter. So if you're one of those students, maybe come talk to me and clarify the distinction there between time and frequency domain. With respect to question 5, those were the quick answer integrals. If you got those wrong, then that probably indicates that you're still uncertain about step functions and impulse functions. So definitely come talk to me about that, because we do continue to use those signals throughout the rest of the semester. So it's good to make sure you're comfortable with each of those. Other than that, like I said, if you have any concerns, come talk to me. You'll see on LMS as grades go in, that is giving you kind of a rough running total. So you'll see a letter grade associated with what has been submitted so far. When we get to the end of the semester, that letter grade that you see is exactly what I copy over into SIS. So there'll be no surprises at the end where you think you have an A and suddenly it's a B plus or something like that. Whatever you see there is what you're going to get. So you have a good estimate of how your performance is. And if at any point you don't like what you see there, then come talk to me. All right, so kind of picking up from where we left off before the exam. So we were looking at Fourier transforms, and we could kind of give a brief overview of what the class was to really show why we've gotten to this point, right? So we had started off talking about signals, right? So ways that we could represent maybe physical things like voltages or currents with respect to time. And we said that these signals, really how these signals are generated, modified, comes from this idea of systems, right? So we have these systems that can act on our signals and generate new signals. Could be things like filters, could be, you could characterize a circuit as a system. And as we were looking at systems, we saw that there was a lot of different properties that we can use to describe these systems. And in looking at these properties, we found there's this very interesting combination, which is a linear time invariant system, right? So linear time invariant systems are actually very powerful systems for us, because what we found with an LTI system is that we can characterize this system by something called an impulse response, right? So we have this impulse response, h of t, or h of n if it's discrete time, and no matter what the input signal is, we can use convolution to get the output signal, right? So all we really need is that one h of t, h of n, to fully characterize this system. And so as we were looking at convolution in continuous time, what we had found is that there's these special kind of eigensignals, we call them, because they're kind of like eigenvectors for matrices, which are complex exponentials, something like e to the st. And so why we call these eigensignals is because if I take a signal of this form and I input it into my LTI system, which is characterized by my impulse response h of t. Since it's an LTI system, I know the output y of t is the result of convolving the input with the impulse response. And what we actually found when we looked at this is that we can characterize this as e to st multiplied by this h of s. Right? So it turns out that we can compute this h of s once, and then for any input signal of this form, we just substitute s with whatever is up in this exponent here. Okay? And so this led us to the idea that we could make this a little bit simpler, figuring out what the output is if our input looks like a bunch of these complex exponentials. So this led us to the idea of Fourier series, right? So the Fourier series applies for periodic signals. And the idea here is that we rewrite the signal as a linear combination of periodic complex exponentials. Right, so this made sense because when we look at EST, we saw that you have something which is like e to the j k omega 0 t, then you're going to have something that's periodic with period omega 0. And so it's fairly easy when we have a periodic signal to write it as a combination of these complex exponentials. And so this works, like I said, for periodic. So the question is, can we do the same kind of idea, write our signal essentially as a combination of these complex exponentials for aperiodic signals? And it turns out that we can, in a way. And we have this idea of the Fourier transform for signals which are not periodic. And so we can write a signal, x of t, and it's kind of like a linear combination, except instead of having a sum of discrete e to the k omega zeros, instead we're going to have an integral, and our scale factors are coming from the Fourier transform at that specific frequency. And instead of having those discrete, we have a continuum of omegas. Right, so we're going to encompass all of the frequencies in order to be able to generate an aperiodic signal. So this equation here is our inverse Fourier transform. And to go the other way, x omega, we take the integral x of t e to the minus j omega t dt. Right, so keep in mind it's an easy thing for people to mistake, especially when they're going this way. They're so used to integrating over t that they get rid of all of the t's and leave the omegas when they're doing the inverse Fourier transform. Right, so if you're doing the inverse, everything should end up being in t. All of the omegas should disappear. When you're going Fourier transform, all the t's should disappear and you should be left with just omegas. Okay. So that's the base definition. And similar to how we had with the Fourier series, what we like to be able to do is exploit some of the properties that these transforms have, so that we don't have to go through this entire integral every time that we have a slightly different signal. And so I'll give you a summary of the properties and then we'll dig through some of those. So our Fourier transform and you'll see all of these too also in your reference tables as well. So the one that we always start with, which makes sense because we derive all of these transforms specifically for LTI systems. So it makes sense that it would satisfy our linearity property. So if I take and do a linear combination of two scaled signals, I would get the same type of linear combination of the Fourier transforms. And I do try as much as possible to exaggerate, right? So if it's a lowercase, I'm going to use that to denote the time domain, and the uppercase to denote the frequency domain. Just so it's a little bit clearer as you're looking through which one it is that we're working with. Right, so we also have this idea of time shifting. So if I take my original signal and I just shift it by some amount along the horizontal axis, then when I take my Fourier transform, I'm going to get a scale factor, omega, which captures that scale factor T0. We can also do a similar kind of thing. And instead of shifting in the time domain, we could also have a shift in the frequency domain. So in this case, you would have your E, J, omega 0 t, x of t, corresponds to a frequency shift of omega 0 in the frequency domain. All right, so definitely one thing that can trip up a lot of people, pay attention to the signs, right? So you can see here we have a minus T0, minus T0. In our frequency shift, see that we have a minus omega 0 and a plus omega 0. Right, so keep in mind where those plus and minuses are, because that's definitely an easy thing to trip up when you're using these properties. We can also do a time reversal. So if I take my x and just flip it across the vertical axis, that is going to correspond to a similar flip in the frequency domain. So one more thing that we could do to our time axis is we can do time scaling, x at, right, where if a is greater than 1, then we're shrinking, kind of squeezing time. If it's less than 1, then we're expanding time. If I do the Fourier transform here, I'm going to get 1 over a, x, omega over a. So you get that scaling both in the magnitude in the frequency domain and also in the frequency axis as well. So the next one, right, so we could linearly combine signals in the frequency domain, or in the time domain. We could also multiply them. So I could have two signals, x of t times y of t. And this turns out that multiplying them is going to get us convolution in the frequency domain. All right, so that kind of ties back to the idea that maybe there's some things that are easier to do in time, some things are easier to do in frequency, right? So here we're just multiplying the value at each t time versus here having to do an integral. But kind of the converse or the complementary, I guess, maybe, of that, and probably everyone's favorite property by the time they get to this point in the course, is that if I take and have a convolution in the time domain, the result is multiplication in the frequency domain. All right, so depending on what your situation is, you could actually choose to operate in the domain where you don't have to do an integral. And a couple other things that we could have differentiation in time. So I take the derivative of my signal, and I'm going to end up with j omega x omega. And I can also do integration in time. So if I integrate my signal, and we're going to take a look at each of these in a little bit, so we'll get a little bit more information about where some of these are coming from. But the integration in time is definitely one that might seem counterintuitive at first, so definitely when we take a look at that one, you'll see where that's actually coming from. All right, so let's start taking a look at some of these in a little bit more detail. All right, so let's take a look first at time scaling. Right, we did look at some of these other ones before the exam. We looked at linearity and time shifting. So let's take a look at the time scaling property. So what this tells us is that if we have an x of t, which has the Fourier transform x omega, then x at is going to result in the Fourier transform 1 over a x omega over a. And we can verify that by looking at our integral definition. So we know that x omega is defined to be the integral of x of t e to the minus j omega t dt. One thing I should note here, right, because we would deal with the time flipping separately. So you treat it as, so if you had something like x of minus 2t, you would treat it as two separate things that were happening at the time scale and the time flip. Similar to how we would if you were doing the signal plotting yourself. So if I look at substituting in, instead of x of t, I have x of at e to the minus j omega t dt. Right, so we want to see if we can get it to look something like this. So what we can do is a change of variables where we're going to have our v be at, which means dv is a dt. So when I do the substitution in, we get x of v, where it was t is now going to be v over a, and where it was dt is now going to be dv over a. Right, so it's equal to 1 over a Right, so we can see the form looks like what we have here. Right, so instead of t, we have v, we have v, we have v. And we can see that instead of omega, now we have omega a. So this is where that x of omega over a is coming from. And we have this additional scale factor out front, that 1 over a. So let's take a look at an example of where we can apply this. So we had computed before if we have x of t is 1 between -1 and 1, so we have a rectangular pulse, and it's 0 everywhere else. Right, so we're kind of taking that idea of where we had the pulse train that was periodic before. We basically took that period all the way to infinity, so we have just one rectangular pulse. And what we found was that the Fourier transform, in that case, our x omega, was 2 sine of omega over omega, which we could also call 2 sinc omega. So now that I've already went through the process and computed this, let's say that I was given y of t, which is 1 between -2 and 2, and 0 otherwise. And we want to know what is that Fourier transform. Right, so we could go ahead and do the integral again and figure out what that is. Or we can take a look at this and recognize if my x of t looks like this, and my y of t looks like that. Really what this looks like is like the original x of t, but we've taken and we've stretched it in time. So y of t is actually x of 1/2 t. Right, so we can see that the width here has doubled, so the scale factor is going to be 1/2. And so I can use my time scale property up here, and we can recognize that y of t, we're going to have 1 over our scale factor. So in this case, our scale factor is 1/2. Now I'll just copy this back down here so we can see what we have going on here. All right, so we substitute 1 over a, it's going to be 2. And we have x, 1 over a, once again, is 2. We have x of 2 omega. So everywhere that was omega in our original x omega, now we're replacing with x of 2 omega. So we're going to get 2 times 2, sinc, where it was omega, now it's 2 omega. So we have 4 sinc of 2 omega. Okay, so saved us all that work of going through and doing the integral again by just using that time scale property, being able to recognize that relationship. So one potentially useful property that I forgot to mention in my summary list is the DC value property. So this is a way that we can figure out what that DC constant is for our signal. So if we have x of t x omega, right? So the DC value is going to be when our frequency is 0. So if we look at our integral, x of t e to the minus j, our omega is 0. And so e to the 0 is just 1. So we're left with the integral x of t dt. Right, so essentially what we're getting is that average of our signal. And what's actually interesting is that we could recognize that if x of t is an odd function, right, so recall that means that your x of t is equal to minus x of minus t. Something like how you have the sine type of property. If you have something of this nature, your DC value is going to be 0. Right? Because essentially what is positive on maybe the right-hand side is going to be negative on the left-hand side due to the symmetry. So you can actually save yourself a little bit of time if you recognize the nature of your signal. You can figure out what your DC value is for that signal. So now we'll get into the two that are maybe a little bit more interesting to look at, and that's the differentiation and integration. So first we'll look at the differentiation property. Okay, so what this one tells us is that if we have a signal and we take the time derivative of that signal, we're going to get j omega x j omega. So let's see where that actually comes from. So we know our x omega is defined to be our integral x of t e to the minus j omega t dt. And so now if I substitute instead of x of t, I have d dt of x of t. So I take the integral of dx dt e to the minus j omega t dt. So actually, we can do this pretty easily using integration by parts. All right, so if we can recognize integral u dv equals uv minus the integral v du. Right, so then we have our dv is this dx dt dt. So our v is x of t, and our u is e to the minus j omega t. And we're evaluating t minus infinity to infinity. And I'll actually write these down here too. So v dv. So that would make our u and our du would be minus j omega e to the minus j omega t. So then we have a minus sign here, those cancel out, so we get plus j omega integral x of t e to the minus j omega t dt. Right, so one thing for this to be able to work out, and is something that makes sense for these signals when we first derived our idea of this Fourier transform, we said one condition that we need is that our signals are absolutely our square integrable, right? Because otherwise we could have problems with this part here, because we have t going to plus minus infinity. So at some point our exponential is going to go to infinity. But if we assume, and this was an assumption that we had for the Fourier transform integral to exist anyway, is that our x of t is absolutely or squarely integrable, then the limit as t goes to infinity of our x of t is 0. And the limit as t goes to minus infinity of x of t is also 0. Then in that case, this x of t e to the minus j omega t, our x of t going to 0 is going to counteract that exponential potentially going to infinity. So as long as we have this condition, which was necessary for the Fourier transform integral to exist in the first place, then this first part that comes about is just going to go to 0. And so we're left with this integral dx dt e to the minus j omega t dt is equal to j omega integral x of t e to the minus j omega t dt. And we look at this part here, and we can see that it exactly matches what we had up here for x omega. So this is indeed just j omega x omega. And so let's take a look at a way that we can apply this property. Right, so let's say we have the same x of t that we looked at before, which is just our rectangular pulse. Right, so if I was to take the derivative of this rectangular pulse, this would be an impulse going up at t equals -1, and we'd have a pulse going down, or impulse going down at t equals 1. Right, so it captures that two step changes that occur for this x of t. So we already have that our Fourier transform of this x of t is 2 sinc omega, or 2 sine omega over omega. And so if I want to take the Fourier transform of this derivative, okay, so what this property tells me is I just multiply the original by j omega. So we have j omega x omega is 2 j omega sine omega over omega. So my omegas cancel out, and we get 2j sine of omega. And so actually with this example, I can verify this another way. I could use the time shift and linearity properties and recognize that my deltas end up becoming exponentials right? Because if you look at your table of transform pairs, delta of t Fourier transform is 1. Here we have a time shift, so we can shift using that e to the j omega, e to the minus j omega t 0. And so we have 1 here, we have a -1 there, and we have the scale factors out front. And we can recognize if we look at our that front table of our reference tables, that this looks like a sine. It's just missing the 2j out front. All right, so we can verify here, right, whether we use one property or the other property, we'll still get to the same result. So that's one of the benefits of having all these different properties that are unique to these transforms, is that whatever way makes most sense to you, there's different ways that you can get to the same result, depending on what your signals are. Right, so the complementary property to the differentiation property is integration. Right, so this tells us that, let's say we have our x of t has the transform x omega, and we're going to define another signal z of t, which we're going to define to be the integral of this x of t. Or another way that we could look at this is dz dt equals x of t. Okay, so you see that relationship between them. So what's interesting about the integration property is that if we look, say, at our differentiation property here, we can see that our x omega is j omega z omega. So probably the first instinct would be to say, well, in that case, then wouldn't z omega be 1 over j omega x omega? And it turns out that that is not the case. Okay, so let's take a look at where we can see that that's not, in fact, true. Okay. So let's take a look at the y of t that we had before. Or different y of t, right? Instead of scaling time, we're scaling the magnitude. My apologies. Okay. So if I have this signal here, then so basically what I've done here is I've taken my original x of t, which was that rectangular pulse, and I've just shifted it vertically by 1. Right, so now instead of being 0 everywhere and 1 between -1 and 1, it's going to be 1 everywhere and 2 between -1 and 1. So if I look at the derivative of this signal, we have a step up of 1 at t equals -1. We have a step down of 1 at t equals 1. And so the Fourier transform here we've already derived 2j sine omega. Right, so does this mean that y omega is equal to 2j sine omega over j omega, right? So that's 2 sinc omega. Right? And the answer there is no. Because we saw previously that x of t had the Fourier transform of 2 sinc omega. So this was the case where it was equal to 1 between -1 and 1 and 0 otherwise. But our x of t is not the same as y of t. Right? So we would have a non-uniqueness issue here when we did the inverse transform. Right? So actually what we have here, another way that we can look at this is if we take our y of t, what this really is x of t plus a vertical shift. Okay? So if I want to compute the Fourier transform of this, what I could do is use the linearity property. And so I can take the Fourier transform of x of t plus the Fourier transform of 1. And so I have my Fourier transform of x of t already. And then the Fourier transform of 1, if we look at our tables, is 2 pi delta omega. Right? So what this means that in general, the true relationship that we have is that if z of t is your integral of this signal, then your Fourier transform is going to be 1 over j omega x of omega, trying to be consistent with my notation here. Right, so this is like what we originally might have guessed based off of this relationship here. But what this doesn't take into account and what we add into here is that DC value. Okay, so this is how we end up with, even though these two signals here, this y of t and x of t, look similar, but they have a different DC constant. And so this part here is going to factor that in. So then when we do the inverse transform, we would get the unique signals back. So let's take a look at an example of using this integration property. So let's say in this case we have y of t is equal to 0 when t is less than minus 1, 1 plus t between minus 1 and 1, and 2 when t is greater than 1. And we want to know what is y omega. So what's actually interesting with this problem is that y of t is not square nor absolute integrable, right? Because we have this constant going to infinity, so if you integrate that, it's going to go to infinity. So we actually can't use the Fourier transform integral directly. But what we can recognize is that y of t is actually the integral of x of t, where this x of t is that rectangular pulse that we've been looking at. And so, since we can recognize the relationship between a signal that we already have a Fourier transform for and this signal that we're trying to find one for, we can utilize this integration property and say that our y of j omega, I'll try to be consistent, is 2 sinc omega, right? So that was our original x of omega. And we need to divide by j omega. And then we also need to have our pi delta omega. And if we substitute in our 0 for x omega, so this 2 sinc was our x omega, I substitute 0, sinc of 0 is 1, and we have a 2 out front. So x of 0 is 2. So it can be a little bit overwhelming at first, and in things like the homework, I'll try and give you hints about which properties might make the most sense, right? Because it might not be immediately clear to you when you just see this, where that relationship could be, what you can actually use as good properties to get you to the solution that you want. As you get more practice, you start to maybe recognize some of the key functions that come up again and again, and kind of start to see the patterns. But it can be a little bit overwhelming at first when you're looking at these wealth of properties and which ones you want to apply at which times. So don't get too worried. We'll have plenty of examples for you to practice with these on. So the next property is probably everyone's favorite, the convolution property, which says if I have two signals, let's say we have x of t and we have y of t, then if I want to take the convolution of these two signals, all I need to do is multiply in the frequency domain. Okay, so let's take a look at this and see where this idea is actually coming from. Right, so I'm going to say z of t is my convolution. And so my z of omega, if I look at the integral definition, is going to be integral z of t e to the minus j omega t dt. And so now I can substitute in the convolution integral, right? So this definition of the convolution here, we have the integral of x tau y t minus tau d tau e to the minus j omega t dt. So it actually turns out that it's possible. And so when you can and can't do this, there's a bunch of deeper level mathematical reasons. But in this case, it turns out that we can actually change the integration order. Right, so instead of doing the integral of tau and then doing the integral of t, we can swap them. And so we can have z of omega is the integral of the integral x tau y t minus tau e to the minus j omega t dt d tau. And so now what I want to do is I want to do a change of variables, and I want to let's say v bt minus tau, so dv is dt. So if I do this substitution, we're going to get the integral of the integral. We have x of tau y of v e to the minus j omega v plus tau. And then we have e to the minus j du d tau. So just doing some change of variables here. And so now what I can do is I can split up this exponential here and bring out everything that's not dependent on v outside of this dv integral. Okay. So if I do that, so my outside integral is tau, so I'm going to bring out x of tau because it doesn't depend on v. We leave yv in there because it depends on v. We'll leave this part, which depends on v, inside of here. And we'll pull out the part of that exponential which does not depend on v. And so now if I look at the inside here, that looks exactly like the definition of y omega. So this is the same as the integral x tau y omega e to the minus j omega t tau. And I can pull this y omega out because that doesn't depend on tau. And I can see that what's left here, that this looks just like the definition for x omega. So this is the same as y omega x omega. So that shows where that relationship comes from, right? Mostly you'll just use that relationship, but this gives you an idea of where it actually comes from, why that is the case that we can do this multiplication and frequency domain for what looked like an integral in the time domain. So let's take a look at an example of using this property. So let's say I have an LTI system which has an impulse response h of t, which is e to the minus t u of t. And we have an input signal x of t, which is the step signal. So we could do the convolution here. We've done this kind of convolution a few times now, and we could figure out what y of t is. Or another way that we can do this is we can use our Fourier transform pairs and properties. So y of t is equal to x of t convolved with h of t. We know in the frequency domain that this is the same as x omega multiplying h omega. So for each of these, if we take a look at x omega first, is equal to the Fourier transform of u of t. And we look at our table of transform pairs, and we see that the Fourier transform of u of t is 1 over j omega plus pi delta omega. And we can do the same thing with our h omega. So this is the Fourier transform of e to the minus t u of t. And so if we look at our table of transform pairs, it's going to have e to the minus at u of t. So in this case, our a is just 1. So we can substitute in a equals 1 into the form that they give us, which is going to give us this 1 over 1 plus j omega. And so now that we have these two individual transforms, to compute my output, y omega. We multiply the first transform with a second transform. And so we do out this multiplication. We're going to get a 1 over j omega minus 1 over 1 plus j omega plus pi delta omega. Right, so this one, where does this come from? So we're multiplying something times a delta omega. So the only non-zero value we care about for the rest of this is where omega equals 0. We substitute omega equals 0 here, and this 1 plus j omega just becomes 1. Right, so that's why we don't have that 1 here. And so now what I can do, now that I have this Fourier transform, is I can look back at my table of transform pairs, and what I'm trying to do is I'm trying to find something here that looks like one of those pairings. And so what I can recognize is that this and this, well, actually you can see this, we already had computed that Fourier transform. So we know that this part is going to become u of t. And then we actually already had something that looked like this too, except we just have a scale factor out front. So this is minus e to the minus t, u of t. All right, so instead of doing the convolution like we had done previously, going through and doing that integral, in this case, we can just use our table of transform pairs, and we can figure out what the Fourier transform is for each of the two signals we're convolving. And we use the convolution property to just do a multiplication in the frequency domain. Once we do that multiplication, then we want to get the result into some form that looks like something we have on the table of transform pairs. And if it's something that we can recognize from there, then we can just use those pairings directly. Right? Otherwise, we would have to actually use the inverse Fourier transform integral to figure out what that time domain signal is. But for the most part, you should be able to just see pairings on the tables for a lot of these questions. Right, so we can take a look at the power of this by looking at the same system. So we have an LTI with the same h of t. And now we have the input x of t is cosine of t. Okay. So our y omega is x omega h omega. So we've already computed our h omega before. Our x omega we can pull off of the transform table pairings. And what we'll see is that we have a pi delta omega minus 1 plus pi delta omega plus 1. Right, so we've actually seen this transform before as well. And our h omega, 1 over 1 plus j omega. So if I do this multiplication out, we get pi delta omega minus 1 pi delta omega plus 1 and so we can substitute in, right, because we're multiplying by this omega, or this delta of omega minus 1. So this is non-zero when omega is equal to 1. So I substitute in omega equals 1. For this case, I substitute in omega equals minus 1, because that's where that impulse is non-zero. Like so. And so what I can recognize is that these deltas here are those scale, the time shifting versions, right? So if it was delta omega, then we have that 1. And so we have a shifting kind of property. So we can recognize from our table of transform pairs that we have 1/2 1 over 1 plus j e jt plus 1 over 1 minus j e to the minus j t. And so if I take and convert these rectangular forms into polar forms, what I'm going to get is 1/2 1 over square root of 2 e to the minus j pi over 4 plus 1 over square root of 2 e j pi over 4 and then I can combine those exponentials. So we have e to the j t minus pi over 4 plus e to the j minus pi over 4. And we can recognize that this 1/2 plus the sum of these complex conjugates here looks like our cosine. So we have 1 over square root of 2 cosine t minus pi over 4. Right, so we've done this kind of problem before where what we had done was we take the h of t, we had found the h of s that corresponds to it, substitute in j omega, where the omega comes from the cosine, into there, get the magnitude and phase of that h of omega, and then use that as the magnitude and phase shift for our output signal. Right, so that way still works. Or you could also use this method of doing the multiplication in the frequency domain and then using the table of pairings to get the inverse transform. Right, so useful thing to know that there's multiple ways that you can get to the same solution. So if there are certain ways that make more sense to you, if you really like doing this kind of multiplication, this makes more sense. If you're really good with doing that h of s kind of method, you can use that. So it's not one specific way that you always have to do these problems. There might be multiple ways to get to the same solution. So all depends on how you like to think about things. All right, so if you want to rearrange and do the multiplication property, show where that comes from, since that's kind of the complementary property to this one. So the multiplication property like I said, is kind of complementary in the sense that for convolution and time, it's multiplication and frequency. What we're going to find is if you multiply in time, it becomes convolution in the frequency domain. Right, so the idea here is that if you have x of t, y of t, multiplying n time, you're going to get convolution in frequency. All right, so let's let z omega be x omega convolved with y omega. So in that case, we would have the integral. All right, so how about instead of tau, we'll use s. Right? So same form as what we had in the time domain, except instead of t and tau, we'll use s and omega. All right, so if I take a look at what the inverse Fourier transform of z omega would be, right? So based on our integral definition, the inverse transform would be 1 over 2 pi, the integral of the Fourier transform, e j omega t d omega. Right, so we'll see something similar to what we saw before, where we end up having this nested integrals going on. So we have integral and another integral, and we have x of s, y omega minus s, ds, e j omega t, d omega. Right, and I can use the same kind of idea that I used before, and I can change the order of the integration. Right, so instead of integrating over s and then omega, I'm going to integrate over omega and then s, so that I can pull this e to the j omega t in with all of the rest of what we have going on. So when I do that, we get 1 over 2 pi. We have an integral and an integral x, y. We're bringing in our exponential, and now we have d omega ds. And so now I'm going to pull out this x of s because it doesn't depend on omega. Right? So first thing that I want to do is look at what's going on inside of here. So this integral y omega minus s e to the j omega t d omega. I'm going to use the same trick that I keep using over and over again. And I'm going to let v be omega minus s, so that dv is d omega. Because essentially what I want to do is I want to find something that looks like the inverse Fourier transform integral. And so to have that, I need to have the argument in here to be a single variable. And that's why I'm doing this change of variables. So when I do that, we get y of v, and we get e to the j vt, e to the j st. All right, so I'm substituting in v plus s for omega, and then preemptively splitting apart that exponential. And so I can pull out the part that doesn't depend on v. we have y b e to the j v t dv. And so this looks like the inverse transform integral here, right? It's just missing this 2 pi scale factor. So this is the same as e to the j s t 2 pi yt. Okay. So we're doing this ends up becoming like an inverse. So in the inverse, it's positive. So if I take and substitute this back in to what I have up here, we have 1 over 2 pi integral xs e to the jst 2 pi y of t ds. Right, so I can pull out my 2 pi y of t because that doesn't depend on s at all. And similar to what we saw for the y case, everything that we have over here is in the same form as the inverse transform here, except that it's missing a 2 pi scale factor. So this is the same as 2 pi xt yt. And so what this tells us is that if we take the Fourier transform inverse of 1 over 2 pi z omega, then we would get xt yt. Right, so that's where that weird extra 1 over 2 pi comes from in this multiplication property definition. Right, so it turns out that as we're going through this process, you could see that there was these 2 pi's that kept popping up from the inverse transform definition. And so it turns out that to get things to match up correctly, we need to cancel out that 2 pi factor. And so we can do that by having this additional scale factor on the frequency domain when we apply this multiplication. All right, so I guess next time we'll start with an example, a couple of examples using this multiplication property, and then we'll go through some other interesting properties. Probably most interesting is the duality property that we'll talk about after we finish up with the multiplication.